Good morning. We're going to finally get started here. As usual, I can't look at the wall, but it's 8:03 by my watch. The class size has shrunk down. Our student that was, actually is a Keysight employee, I found out, because I met with him last week. He's decided he doesn't have enough time to stay in the class, so now we're down to 2 people. No fears, no worries, none of that, because we're already way past the census date and all of that stuff, and it's now a permanent record. I mean, as far as I'm concerned, the class size was thus and such, and if it shrinks, I'll just say I'm used to that. It just always happens, and I'm not saying it's because I'm being too hard or people are being too lazy. It's just there's always factors that come up, and classes move around a bit. So this morning I pushed up set number 3, and I put up a partially updated version of the Jupyter Notebook for Chapter 9. It turns out it has a lot of simulation stuff in it for digital comms, and I got stuff that's broken in there. I was playing with it, and it was bringing Jupyter Lab to its knees. It was spinning lots of cycles, so you're going to have to be careful. One of the things I'm just going to say in the video, I guess, is when you load that notebook, do not try to run all of the cells in it, because it will fail. I mean, it takes too long. We'll probably be looking at it today, but we won't be getting that far down into it, and then hopefully I'll get back to it and clean it up. It does have some digital comm developments in it that are not part of the Scikit DSP digital comm. So it's not within that module. There's stuff that I've added onto it. But the other thing is the notebook needed to be updated because my co-author, Charanth, has gone through the code and cleaned things up for me, which means he's changed some of the syntax, but mostly what he's done is if I use capital, like I have a function called Gaussian noise, white Gaussian noise, I had capital WGN, and he decided to be consistent with Python syntax and make it lowercase. So a lot of times what he's done is he's taken my old syntax, and if I had a couple capital letters in there, like Q function was capital Q, and made it lowercase q. So it's throwing me off because I'm like, what do you mean this function doesn't exist? I wrote it, but it's just in there with a different case typically. So I see while I was talking, it looks like, my viewing tool crashed, which is seemingly was happening a lot last week. It didn't happen at all on Wednesday's class. The good thing about it crashing is it always comes back up to where I was.
Question, Professor.
Yeah.
So the notes didn't seem to be text searchable. It seemed like it somehow got flattened into an image, like I tried to Control F or something, and it doesn't match at all. Can you look into that and try re-rendering them, or is it just...
If you want to, I mean, I can. I mean, right now I've got, trying to think what's in my preamble for LaTeX.
And I guess the table of contents helps, but still, there are a couple of times I was trying to search. Maybe you can try searching and see if it works.
Yeah. All I know is that this is in here, but I don't know. I mean,
if you try to highlight the text, you'll see it doesn't seem to be text.
Yeah, this tool, although it doesn't work like Acrobat or some other PDF viewer. I know what you're talking about. If you know what the preamble is, because maybe it's just a matter of adding one line to my preamble.
Okay.
In
I'll look
LaTeX.
into it and I might just Slack you.
Yeah, and then I can just re-render it. All I'd have to do is rebuild it. So what I did, more rambling here, is I've been writing these notes over many years, so as I've been upgrading the features into them, typically what I do is I also, besides writing new content, I've updated to have links put in, so I'm using what's the package in LaTeX that allows you to have hypertext. So I added the hyperref package in more recently, not just this year, but so those things came sort of in across the timeline. So yeah. If you Slack me in either case, you'll remind me to go take a look at that. I'm guessing I can do that with just a preamble command.
Yeah, I would guess so.
And I'm using PDF LaTeX. So PDF LaTeX supports that, then that would be perfect for me. So we will transition over into the next chapter later on today. And we'll actually be in digital comm. So we had gone through noise equivalent bandwidth. We were going to be looking at narrowband noise, and I started to build a little simulation of that this morning, but I didn't really get too awfully far, and I don't think I'm going to try to do it in class, but I'll try to give you the ideas of what you could do if you wanted to do something like that. So typically in RF communications, we don't have noise that is flat across the entire spectrum. In other words, it's not strictly white noise like we were talking about back over here, this scenario here, where essentially in the RF band, the noise is flat, and we have this model right here for the autocorrelation, and then the Fourier transform of that is a constant n naught over 2 over the entire spectrum. We don't even come close to that in the RF communications domain, but what we do come close to, though, is having it still look in the neighborhood of the carrier frequency as being white. So the model that is used then, and the model that we have to use, we have to have a model in order to represent how the noise impacts the system. So it's called the narrowband noise model, and the bandwidth B is assumed to be much less than, much less than the carrier frequency. Of course, this is going to require some startup. So B is much less than F naught, but it doesn't mean you can't build a simulation, so that's what I started to do briefly. So the expression for N of T in terms of low-pass processes is this equation right here. It would be a in-phase term, NC, and the C is for the cosine omega naught T plus theta, minus NS, which is the S is for the sine, but if you don't like that symbol, what we end up doing here before too long, we end up having things like I and Q for in-phase and quadrature. But the book's notation is C and S. And we'll see how that comes together here in a bit. So the equivalent envelope of our narrowband signal is R of T, cosine 2 pi F naught of T plus phi of T plus some theta. So the phi of T and the R of T are the time-varying envelope and time-varying phase as a result of the additive noise model. And that's down here. This is the one that gets talked about the most, the envelope, in terms of the noise model. So there's what it would look like, and I was going to try to build up a little miniature version of a simulation where you see that the envelope is definitely fluctuating and has that nature of it being carrier cycles inside of there effectively, but random amplitudes because of the noise, effectively noise modulating the carrier, the in-phase and the quadrature carrier. So the assumption is going to be we're going to have white Gaussian, or we're going to have white sense stationary noise is going to be in this baseband, in this bandpass model for the noise, and then that means that because n of t is wide sense stationary, then the in-phase and quadrature terms are also jointly wide sense stationary. So if we go ahead and try to get the relationships now between the autocorrelation functions, we'll abbreviate NC as the autocorrelation between the cosine or in-phase and itself, and NS is also going to be the same quantity because of the symmetry. And then we have the cross correlation between the in-phase and the quadrature components. Now, this may be true, but it's also true that it's not equal to zero. Under certain circumstances, the cross correlation between the in-phase and quadrature is going to be equal to zero. And that's the most interesting case for us. There's a homework problem that you have in the new problem set that, as you kind of look at this, it just depends on the structure of the receiver front end. If you have a symmetrical situation, then it's zero. If it's not symmetrical, then it has a small component. Going back to construct the autocorrelation of the bandpass noise, we can just build that up from the modulation again, the cosine and the sine. And I'm not going through the details of the math at this point, but it could be done. And this is the block diagram that corresponds to how you decompose the bandpass noise into baseband, in phase, and quadrature. So it's assuming that there's an ideal low-pass filter, and really that low-pass filter is not part of the assumption in the real-life system. It's just sort of, it's to get this representation to be useful for modeling purposes. So what you should be thinking of when you see that low-pass filter is that it's just simply to keep the component around zero frequency after the multiplier. Because when you multiply a signal times a cosine, you're going to get, in this case, if it's the bandpass noise, you're going to get a component of the noise shifted up to twice the frequency, and then a component in the neighborhood of baseband, not necessarily centered right at DC, but so that low-pass filter is just to pull out that component and throw away the 2 omega naught component. Does that make sense? It's just it's an artifact of the simulation. Sometimes it's called a zonal low-pass filter, just like in sampling theory, where you undersample, you'll have these different zones where the aliases occur. So we'll call it zone 0, zone 1. Is that a term that you use in your group? I'm just curious.
No,
Zones.
but we do this stuff, but not with those terms.
Okay. I hear people, I was watching a tutorial for a software-defined radio that I have, and it was at the GNU Radio conference, and the guy that was lecturing was talking about zones, and also last 2 weeks at Xilinx thing that I attended virtually, there was a guy talking about their new RF SOC, and he was a professor from England, and he works with Xilinx a lot, and he was using the same term, zonal, whatever. So this would be the zeroth zone, if you wanted to use that terminology. So now what we're now the statement is that the mean squared error between n of t and the narrowband model is 0. So that just means if we synthesize it or we analyze it, whichever direction we're going to go, it will be it'll be exact in the mean zero in the mean squared error sense, meaning that the error between the original and the synthesized one through this process will be exact. And that's important because it says if we're doing all our modeling with the baseband noise, we want to know that it's really true to form and we're not off by an epsilon. We're actually, that epsilon goes to 0 in the mean squared error sense. The properties that are useful to us are those of the baseband terms. So the mean is 0 for both the cosine and the sine. The variance is sigma n squared equals sigma nc squared equals sigma ns squared. and that is N, and that N is, I think if I go back over to here, guess it's not in here. I was thinking the spectral density was in here, but I think it is in here because it's N, or it's N naught over 2. So we'll get back to that again. I always get a little bit confused with the scaling on here. I'm pretty sure, though, I'm just going to step right out and say I think that this is it'll be N naught over 2, but then when we appropriately scale it by the noise equivalent bandwidth, we're going to get N over 2. And then the combination of the powers at the negative frequency and the positive frequency will be N, and that's the variance. Remember, variance has units of watts. You have to just keep thinking that way. Spectral density has units of watts per hertz, so this N naught over 2 is at units of watts per hertz, right? But then over a bandwidth, it's like putting a rectangle on there and integrating it, and we have 2 of them in this case, so that's where the 2 is coming from. So the in-phase and quadrature terms have the same N or same power. And if we go back in the other direction and want to synthesize the power spectral density of the RF noise, we can do that in the frequency domain by just putting up translates of the in-phase and quadrature terms. So we shift it up, shift it down, and then we have the difference between the cross spectra if they do exist. And I've got some pictures coming up here that'll help explain what's going on there. Furthermore, we can look at the synthesis just of the, rather than the, what did I say, analysis, the synthesis is taking it back to baseband. So writing it in terms of the bandpass components, we can get the low-pass components. And the cross-spectral components will look like this. These are things that you'll be doing in this particular homework problem. The reason why I'm spending time on this and the reason why I'm giving you the homework problems, though, is everything that happens in wireless communications really sits with this as its foundation for the noise process. So it's used, and it doesn't get talked about too much from here on out. It's just like, oh, we're going to do the same thing, and this is where it comes from. The thing that we'll have to keep in mind, and I think you have to keep in mind if you're going to be doing this stuff on the job, is that there's so much that goes on with digital comm these days that you'll be looking at a spectrum analyzer, you'll see the received signal, you might put in some additive noise to perturb it, you want to measure the noise power at the receiver front end, and then you'll get on into the receiver, down convert it, and then it will be at complex baseband because that's the way digital comms works with DSP. And then you'll get into an issue at some point where you're trying to reconcile the scaling and the noise power levels and things like that. I mean, and this is the problem that it's a classical problem. If you make the mistake, you're off by 3 dB. So you've heard people maybe in the past talk about 3 dB errors. It has to do with scaling and things like this. You just get yourself confused and then you don't remember things properly. So I'm going to try to help with that, but I still have that problem. If I'm working with somebody and it's a real world scenario, we'll quibble over, is it this or is it 3 dB more or 3 dB less, because you get yourself kind of twisted around as to which side you're dealing with, which is why I was thinking I should make up this narrowband noise model on the computer just so you'd have something to go back and play with. Okay, one of the things we can observe about the cross spectrum is that it is going to be equal to 0. That's what this, identically equal to 0 if no, I didn't say that right. Not it. it is identically equal to 0. If that's so, then NC and NS are mutually uncorrelated processes, because it's saying that the cross spectrum between them is 0. But the important thing is that only holds when N of t is symmetrical about F naught. Then another aspect is if N of t is Gaussian, then the symmetry condition makes the joint PDF between the in-phase and quadrature noise components appear independent, because uncorrelated implies independent for Gaussian. So then this is the joint noise PDF of the baseband noise processes. This is going to be used in modeling for sure. When it's not symmetrical about N naught, then there is a cross spectrum that's non-zero, but one of the things it still holds is that at the lag of 0, tau, in the autocorrelation function, it still will be 0 there. In other words, a property of this cross correlation is it'll always be such that at 0 lag, it's equal to 0. And we're going to see a picture of that in just a second here. Just another note along the way is that if you look at the envelope and phase function of this joint PDF, it's going to have a Rayleigh PDF for the envelope, and then it's going to have a uniform distribution for the phase. This was talked about when we were looking at jointly normal random variables, remember? Rayleigh and uniform. And we'll be getting into fading in a channel 2, which is a multiplicative effect, but that's where Rayleigh and Ricean and other PDFs come up. So this is a general picture. I guess I'll just make it a little bit smaller. That's a general picture of what we've been talking about. The orange colored one on the top, it would be like, I drew this to look asymmetrical, and I made it very asymmetrical because I was just trying to emphasize this is in general what it looks like. So if we were to go form, according to the formulas we just looked at, the in-phase or quadrature noise spectra, it would be the second plot down. So it looks like we're adding two of them together. So what we're doing is we're taking the spectrum and then flipping it so that when they combine together, or effectively what happens, yeah, that's what happens. So that's the in-phase component, and then the quadrature, the cross-spectral component looks like the difference. So you see the little ears sticking up, positive and negative. And then if we take that down to baseband, we just have those components centered at 0 for the in-phase and quadrature, and then the cross-spectrum. So just emphasizing what I already said, the second bullet there just says that still uncorrelated at tau is equal to 0. So suppose now that we have symmetric Gaussian random process, so now we're just going to take the simplified case where it's perfectly symmetrical. We have some IF bandwidth BIF, and it's centered at F naught and minus F naught. And then if you go ahead and look at what's happening at baseband, we have this perfect rectangle and then nothing for the cross spectrum because it's equal to 0 for all frequency. And if you go ahead and integrate, we want to get the power in n, we integrate that or set tau equal to 0 in the autocorrelation function. We're going to get, and this goes back to what I drew on that picture, we're going to have the spectrum, which is n naught over 2, and then we're going to have the upper and lower pass bands, each of bandwidth BIF, so there's 2 of them, so then we get N0 times BIF. Second start. All right. And then the cross, or the in-phase and quadrature components are the same thing. Each is N0 times BIF. This is the way the model is built up. You might, this is where the 3dB confusion arises, is why isn't each of the in-phase and quadrature half, so that when summed together it's N0 times BIF. This is just the way the model is built. So this is where you can get confused, though. I don't know, maybe you're not confused at all, but I get confused because I say, why did we do it this way? And then I'm pretty sure I'm going to realize, oh, this had a reason, but I can't think of it right now. Otherwise, you're thinking, if the RF has this much power in watts across the entire spectrum, why don't we have the same total power in the in-phase and quadrature parts brought together? Right now, it looks like there's the same power in each component, so you'd think the total noise power is going to be twice that. Okay, cross spectrum is 0 under this case, and then we can write out what the PDFs are for each of the components, NC, NS, and then the joint PDF for the joint distribution on NC and NS. We can then simplify, or we can then apply the equivalent noise bandwidth ideas. So if you've got a typical IF filter, which might have some ripple in the passband, this is very highly emphasized, but just to say that it's not perfectly flat and the skirts of the filter are, finite rather than zero width, dropping down like an ideal filter. You can then define the noise equivalent bandwidth for that situation and use BIF as the noise equivalent bandwidth in the definition. So the BIF here would be the noise equivalent bandwidth for the receiver front end, and this would more than likely be the way the receiver has been specified. Let's see. Come on. So their BIF is not a 3 dB bandwidth. It would be a noise equivalent bandwidth. So if you were modeling and you were working with a front-end engineer that says the bandwidth of the receiver is, say, 5 megahertz, it's fair for you to ask the question, is that the noise equivalent bandwidth, or is that some other definition of bandwidth? If it's noise equivalent bandwidth, then you're good to go with all your analysis. If it's not, then that engineer has to tell you what the frequency response is of that IF, and then it'll be up to you to just numerically integrate it, like is in the top line up there, to get the noise equivalent bandwidth. Does that sound reasonable? It's like you want to make sure, because if there's a difference in there, you want to make sure you take that into account. Why is that important? Well, it might only be a few hertz, rather than being 5 megahertz. If it was a noise equivalent bandwidth of 5 megahertz, the 3 dB bandwidth would probably be less than that. Say it's at 4.9 megahertz, but then because of the skirts going out, it's going to make the noise equivalent bandwidth slightly greater. It just depends. But systems are spec'd usually to within fractions of a dB of their operating point, so you don't want to come up with an analysis that's incorrect theoretically. There's also some things to consider in the discrete time domain. So if we're working with digital signal processing front end, which is pretty much universal these days, but simple systems still could be all analog, then we're going to have a random process X of n. All the random process ideas we've talked about still apply, And so suppose the baseband noise gets filtered by a low-pass filter to the Nyquist frequency, which would be 1 over 2 times the sample spacing. The spectral density in this model would still be n naught over 2, but it's in the Nyquist band. So if we inverse Fourier transform that spectrum, assuming it's flat over that Nyquist band, this is just a simple analysis. It might be varying. It might be rolling off before the band edges in the Nyquist band because you're oversampling, let's say. But if it was flat across the band, then you get a sinc function in the autocorrelation function. And if you look at sampling right at the Nyquist rate, 1 over t, then an interesting thing results, namely that it looks like it's white noise, just because it filled the entire Nyquist band, and then because of the sinc function in here, it's going to make it appear to only be activated at k is equal to 0. K is the replacement for tau in the discrete time domain. Otherwise, it's just close to that. It's still pretty white. I mean, white in the sense that it's peaked right at 0 and then it's small after that. Is that making sense too? Just nice assumptions to make, or nice properties to go with. Okay, last thing that's in this chapter is a little discussion about the Ricean PDF, and this gets ready for a discussion of fading that will be coming up later in the next chapter. So a simplified preliminary analysis of fading might just be on an unmodulated carrier, and then you would have a sum of randomly phased sinusoids plus, so there's a plus sign in here, plus band-limited Gaussian noise. So here's the model then. We have a specular component just at a fixed frequency f naught, and then we also have the narrowband noise model coming into play, and that's representing the fading path, the diffuse path that arrives at the receiver as well after it's gone through a bunch of multipaths. So we'll assume that A is a constant and theta, because of the number of arrivals, we're going to assume that it's uniform on the interval 0 to 2 pi. So they're called specular and diffuse component. This is the setup for the Rayleigh fading channel. So we have a direct ray from the signal, and then we have a diffuse set of components. I'm going to try to draw a picture to say that we've got that, and then we've got all kinds of other tiny components arriving at from different arrival angles. And if we expand all that into in-phase and quadrature components, then we can take the direct path or specular path and break that up from the trig identity into a cosine theta minus a sine theta, and then times the expansion frequency cosine omega naught and sine omega naught. Then bring those together into an envelope in a phase that comes out of this. So now we have a specular and a diffuse component in each one. The diffuse component is modeled simply as Gaussian noise because there's so many components that are arriving due to reflections off of objects and things. And then same for the quadrature side. And then that comes together then to say, okay, the envelope is composed of the square root of the sum of the squares of the in-phase and quadrature components. But now each in-phase and quadrature component has a constant term, a cosine theta and a sine theta, plus the additive Gaussian term to model the thetaing aspect of it. So this can take us back to the rectangular to polar conversion that was done in the random variables chapter. And then we can suppose we're interested in the envelope fluctuations, which is what this example is all about. So we integrate out the unrounded variable phi in order to obtain the PDF on the envelope. And when you do that, go through that math, the integration, that's an integral that you have to look up in a table. It will be an integral from 0 to 2 pi, right? That'll be the angle that you're integrating over. But when you integrate out that joint PDF with the substitutions to get the envelope, so this is the variable transformation stuff, you'll end up getting this Ricean PDF, as it's called. So it has this I0 Bessel function in it. And A is the amplitude, R is the random variable itself, and this is how we arrived, this is where I0 comes from in the tables. It's a modified Bessel function. And it's available in MATLAB, of course. I'd never added this in Python. It's available in scipy.special for special functions. I think I pointed out that if you don't want to use the statistics module from SciPy, like I showed you, and I really would rather use that because it's a lot more comprehensive. But within scipy.special are all these special functions like the error function, complementary error function, all the Bessel functions, hyperbolic, elliptical, and so on and so forth. I've tapped into special on quite a few occasions when I was doing this acoustics modeling for a spherical head under a plane wave arriving at the spherical head. It was a boundary value problem for acoustical pressure waves, but not unlike EM waves. And all the special functions that I needed, I discovered were actually in that dot special. So it's pretty handy. It's actually very nice, I think. So, and now I made it pretty obvious, but let me just jump over here for a second. So I just imported special and then hit the period, hit tab, and it should catalog. Wait a minute, I didn't put in the abbreviation. I should have made it special, but let me do this again. So these are all the special functions, and so I've typed in I0, notice that, and then I put a parenthesis, and then I did Shift Tab, and it's just telling me what the signature is for that Bessel function. It says modified Bessel function of order 0, and then you'll have a bunch of notes in here. So when you're actually dealing with this in a model of a Rayleigh fading channel, with both specular and the diffuse would be the Rayleigh part, and the specular makes it Ricean, so it's shifting the component. And when I say shifting, I'm thinking in terms of X and Y here. It'd be like if we were modeling the impact of a channel, we would just have NC and NS if it was purely diffuse and assumed to be Rayleigh at that point. And the reason why it's said to be Rayleigh is because the envelope of that two Gaussians that are uncorrelated at that sample time will be Rayleigh in envelope. And now if we add in the specular component, we get that constant, so we're shifting, we're effectively biasing over the Rayleigh component with the A cosine, which is related to the envelope or the strength of the envelope, and then it becomes Rician. So that's this PDF for the envelope, and because the ratio of the power in the specular component to the power in the diffuse component is a measure of how strong the specular component is relative to the diffuse component. The book uses K as that ratio, A squared over 2, and then divided by sigma squared, which would be the power in the specular or diffuse part. So when I did this a long time ago, I used Mathematica just because I was using that. I still have Mathematica. You can have Mathematica if you want to play with it. It's just another tool to use, though. CU students get to download Mathematica for free to use while they're students. At any rate, I just plugged it in here directly, and really the notation is not as important to me as just seeing what does it look like. Here's what the PDF looks like. The Rayleigh PDF, all the PDFs of the envelope are going to start at 0 because they're non-negative. The square root is going to be non-negative. So, but the Rayleigh has its first peak somewhere between 0 and 2 in this normalization, and then as K, specular component, gets bigger and bigger, it shifts out away from 0, and now it looks more like a Gaussian for large K. And of course, when K approaches infinity, which doesn't mean the power is infinite, it just means that the Rayleigh component is 0 or very tiny. What's this going to become? Just seeing if you're thinking. Rather than be a Gaussian bell, as it shifts out further, it's going to be, the variance will be tighter, and then it will look more like what?
An impulse.
Yeah, an impulse. So it'll be an ideal non-faded channel. These are the moments. This is the second moment, mean square value of the envelope. So this gives you an idea of the fluctuation and the variation about, so it has to do with the deviation about, actually this is the central moment, or the non-central moment, so it has to do with that overall deviation. Okay, done with that. So I'll just say what I was going to do. I'm not really going to do it, but what I was going to do, and I think I might still do, this keeps me from grading papers, by the way, when I tinker around like this. I was going to construct a filter. I was going to use the package that I have, FIR Design Helper, and I was deciding to use Remez, and I was just going to build up a bandpass filter, and then I was going to build up a low-pass filter to synthesize the low-pass components, and then I was going to put some Gaussian noise into it, and then just look at the envelope, and then look at the scaling of the noise in the baseband form and in the RF form. So let me just do one thing to show you how we could get here. So I'm going to go into here. This is the way this Remez function is set up for the low-pass version. Rather than building a bandpass filter, in this case, I was going to want to have the exact same filter in the low-pass domain as the bandpass domain. So I was going to build it up as a low-pass. So I was going to set my sampling rate to 10. It could be 10 megahertz or whatever. I'm going to do that, and I'm going to put the passband is going to be at 1. I'm just pulling this out of my head. I'm going to put this at 0.1 or 0.2, let's say. And the stop band is going to be at 0.4. Then I have to put in the deviation in the passband. I'm going to say that's going to be dB 0.1. And then this last parameter, the stop band attenuation, I'm going to say that's going to be, I'll just set it at 60 dB. And the last parameter in here is, do I want to bump the order, because this is an approximation equation to get this equal ripple filter, but I'm just going to plug in the default so I can change it if I want. And then what I should have done, because I don't have something that the student also added for me, was status, so that this function, status is set to true, but I have to go into the package that incorporates that so I can have it report the status. And the status is that I had created for this function when I originally did it was the order of the filter, but I can cheat and just do this. And then when I run this cell, it's going to give me the order of the filter. So it's 130 low-pass filter. And furthermore, just cannibalize that for now. If I wanted to plot of it, get a plot of it, I've got a function in this module. It's called freq_z response list. So I can use the freq_z function, which is part of SciPy, and inside of here, then I can put in a list of filter designs. And this function was created by me, so a person could overlay plots of a bunch of candidate filter designs they might have created. Like, let me look at several of them. Change the ripples, change the type. So I have to put in a list in here, so I have to put it in square brackets, Python list, so it's going to be B sub LPF, and I don't have another filter, but then the A coefficients for the ratio of polynomials in the Z domain, this will just be 1. And then I have to specify what I want to have it plot. I'm going to have it work in dB. And then, oops. And I need to put in FS will be 10, and the other two I'll just leave as defaults. And chances are I don't really want to have that much dynamic range plotted, so I'm going to go ylim, go down to about -70, go up to about 2 dB. So there's my filter, and if I was to put a grid on that, I might want to tweak it slightly, because it's not quite down 60 dB, so I could go back up here at this point and I could tweak it, or I could compare it and have multiple filter designs, but it came out pretty close. And now if I want to get a bandpass filter out of that, suppose I would like to set the passband up here. If I want to model this within DSP, I can make this look like a bandpass process. Where do I want to put the carrier? I'd like to have it well above this action up here, but I can, where do you think it should go? Should it go right in here at 3.5? I mean, I can certainly do that, so. Pardon me? Or 4? I mean, I'll just do it at 3.5. So first I need to have a time axis, and that's just going to be the length of, well, I have to create a length. Samples do I, well, no, never mind.
Wouldn't you just multiply by cosine?
Yeah, I am. I'm getting an index, though. I'll just call it NN. After multiply,
Just enumerate.
I could. I'm just going to do it without it having a loop, though. I'm just going to do it this way. Let's say A range is length of B sub low-pass filter, and then I will form B sub bandpass filter is equal to B sub low-pass filter times cosine of 2 times pi times 3.5 over 10 is my sampling rate, and then times NN. I'm going to go back up here, not perfectly good form, but I'm going to go do this. I'm going to put B sub BPF. There's the filter. The amplitude is reduced because I've shifted it to positive and negative. I'm only looking at half the plot of it now. So according to the way the synthesis works, though, I'd have to synthesize that with an amplitude of 2. So I'd have to do some scaling in here. But now what I can do, though, is I've got a bandpass filter designed, and I can go ahead and pass some white Gaussian noise through it, and then just play around with calculating the power at the outputs of the filters. And then I can do the in-phase and quadrature parts and so on to synthesize it back down to complex baseband. Complex baseband means this filter will be used to obtain in-phase and quadrature noise, not just the real part. I just synthesize the filter using the real part, but I actually have to have the two components. But I'm going to carry on with that myself. I just wanted to give you a little idea about how you could build up things if you're needing to build a simulation or something. Most of the time, we won't do this at all. Everything will be treated right down there at baseband. It might deviate about zero frequency, but we're not going to try to create a carrier-based system. We're going to model everything as if it's down at complex baseband, which the DSP domain just means the front-end receiver has complex frequency shifted the signal from a high-frequency carrier down to something very close to zero. It doesn't have to be exact. It's just in that neighborhood, and then it can go get processed at the front end. Okay. Before I move on, there are a few, I would say, relatively simple problems here remaining from the random process chapter. One of them's noise equivalent bandwidth. One of them's in-phase quadrature, bandpass noise. I think another autocorrelation. I don't know, I was reviewing them again last night. So those top this set number 3, and then we're into the next chapter. We skip over 8 because that's analog signals and noise, and then we start with digital modulation in chapter 9. And we're going to be looking at simple binary scheme, and this problem right here, it's got bonus points on it, involves trying to find the optimum threshold, which is derived in the book, but it's left out. The details are left to a homework problem. So the optimization that's involved in this problem involves Leibniz rule for differentiation of a definite integral. And it's used if you want to carry this out. So principles of data transmission in noise. There's also like I said, there's a notebook for that, which I was eating breakfast. I worked on it, but I didn't get it done. So you can't run this notebook. It'll run run into a really long calculation, but I should be able to open it. It has a bunch of graphics in it, though, which is probably going to take it a while to open. I'm just going to keep it handy so I can jump back over here to it if and when I need to.
Sorry, for that homework problem, are you saying the whole problem is extra credit, or are you saying do the problem and then there's an extra credit section to it?
I can get over there. What does the problem say? I can't. I mean, what was the problem number
Or
again?
if you can, like, clarify that.
Yeah.
At some point and re-upload it or
Yeah.
flag message.
No, I think it's the whole problem is finding that optimal threshold. If I could reach my book, I just don't want to disconnect my microphone. I'll look at it during break and I'll answer you after break on it. So if we go into chapter 9, now we're into the business of digital communications, and mostly in a white Gaussian noise channel. That means additive white Gaussian noise. And then we have the potentiality for distortion caused by some linear filtering process that's not quite what we wanted. What is it about this pen and this tool that, there we go, linear filtering, carrier phase, and simple timing errors. Those are some of the main things that we'll start by developing once we get into the modulation. We'll be able to model impact to carrier phase noise as well. And I think that's in one of the homework problems, actually, where you're going to be doing some modeling with the phase noise configuration. So typically we have a digital source. It could come in as an analog source. We'll have an encoder, and that comes up in chapter 11 of the book, convolutional and block coding. We're going to be focusing on modulator, demodulator, detector, and just analyzing then what comes out by looking at error probabilities. The decoder is paired up with the encoder, and that's chapter 11. The channel will be talked about too, because we'll be talking about channels that would have fading, slow fading, fast fading, and then also we could have interference from adjacent signals or co-channel interference.